Hello, our viewers. Previously, we have tried to discuss about some main points about vectors. Today, we'll proceed on that. Previously, we have tried to see that the definition of vector, the different types of vectors, and as well, we have tried to see about the operations of vectors, how to add and subtract vectors using geometrical and analytical methods. At last, we have seen about cosine law and sine law. And today we'll proceed on that. Let's try to solve one good example and we'll try to see about vector multiplication. Here we have a good example. It says that suppose two forces which are 30 Newton and 40 Newton acts on 4 kilometer load at an angle of 60 degree. What is the resultant force using cosine law? It's possible to determine cosine using cosine law, component form. We have different techniques of finding the resultant vector. And here it says, let's use a cosine law to determine the resultant vector. The two forces which are acting on a given body is 30 Newton and 40 Newton. Therefore, how do we determine the resultant vector? Cosine law states that f1 squared plus f2 squared plus twice of f1, f2 cosine of theta. This is how we determine, or this is how we apply cosine law. Therefore, we have 30 degree squared plus 40 squared plus twice of 30 plus times 40. And the angle between the two vectors is found to be, or given already to be 60, cosine 60. Therefore, the resultant vector is 60.8 Newton. This is a net force which is acting on the object. 30 Newton is acting on this direction and 40 Newton acting on this direction. So the resultant force becomes 60.8 Newton. Let's proceed. And how do we determine the angle? Previously, we have said that the angle of the resultant vector can be determined using sine law. Okay? Therefore, here we have the angle which is 60 degrees. 60 degrees is the angle between the two forces. It's not the angle between the resultant and this force. Therefore, here let's say that we have phi and we have 180 degree, which is, here we have 60 degree. If this is 60 degree, this is a straight line. Therefore, if this is 60, this will be 120. It is supplementary angle. We are asked to find phi, for example. To find the angle phi, it's possible to use sine law. How? Sine law states that sine phi over the magnitude of B, sine alpha over the magnitude of C, sine beta over the magnitude of E, the opposite sides that we have already previously discussed, is equal. Then it's possible to use sine phi. Let's see the sine phi, 30 Newton. And here you have 40 Newton, sine 120 over, the opposite is R. And here you can find like beta, for example. If this is beta, sine beta over the opposite is 40 Newton. This is what sine law states. Therefore, let's use sine phi over 30, sine alpha over 16.8 is the resultant force, and sine beta over 40. Therefore, alpha can be determined using this concept. It's possible to use this. And at last, beta is 34.7 degree and phi is 25.3. So phi can be determined to be 25.3 degree. This is how we determine using sine and cosine law. And today let's proceed on that and try to see the vector multiplication. So far we have tried to see how to add and subtract vectors using geometrical and analytical methods. The summation and the difference of two vectors is always result in vector. The summation of two vectors gives you vector. The difference of two vectors as well gives you a vector. The difference of two equal vectors gives you 0. 0 itself is a vector. We have said that a null vector. So let's see about how to multiply vectors. The multiplication of two vectors might result in vector or might result in scalar. Okay, it's not like the summation and the difference of two vectors. The sum or the difference of two vectors result in vector, but the product of two vectors might result in vector or result in scalar, depending on the type of the products. So here you have two types of products: the dot product and the cross product. The dot product results in a scalar, and that's why it's called scalar product. Suppose here we do have two vectors. Let's say that vector A and vector B. And vector A can be given using its vector notation form, x in the I, ay in the j, plus az in the k. Vector B can be given as bx in the I, py in the j, and bz in the k. Therefore, the dot product of these two vectors, when we use dot product, the resultant is given to be the magnitude of A, the magnitude of B, cosine of theta, where theta is the angle between the two vectors. These two vectors might be represented like this. This is vector A, and this might be vector B, and the angle between them is theta. Therefore, the dot product of these two vectors gives you the magnitude of A, magnitude of B, cosine of theta, and this is a scalar product. And theta is the angle between the two vectors. Now look, let's try to find the dot product of the unit vectors. Previously we have said that unit vectors along x is not termed or represented using I. A unit vector along j is k, along the y axis is j, and the unit vector along the z axis is k. Let's try to find the dot product of these three vectors. Suppose, what is the dot product of A dotted with j, I dotted with j, I dotted with k, or it's possible to find j with k, or itself I dotted with I, j dotted with j, k dotted with k. Here we have I, j, and k. All of their magnitude is unity. We know that they are unit vectors, therefore their magnitude is 1. Theta is the angle between each one. That means, for example, if the angle between I and I is 0, since they are acting all along the same direction, the angle between I and j is, since they are perpendicular to one another, I is acting along the x-axis and j is acting along the y-axis, the angle between them is 90 degrees. So therefore, let's try to determine I dotted with I. I dotted with I is a unit vector, the magnitude of I, and the angle between those two, I and I. I is acting along the x-axis, I is also acting along the axis. They are overlapping one another, which are acting along the x-axis. Therefore, it gives you 1 times 1, and the angle between them is 0. Since they are overlapping one another, the angle between them is 0. Therefore, cosine of 0 is 1. Therefore, when you multiply this gives you 1. Therefore, I dot I gives you 1. The same is true for j dot j. K dot k is also gives you 1. And don't forget this point. I dotted with I, j dotted with j, k dotted with j is always gives us 1. But if we are trying to dot I with j, I dotted with j, okay, the magnitude of I is unity, the magnitude of j is also unity. But the angle between them, cosine of theta, is 90 degree. Here we have 90 degree. Theta between them is 90 degree. And in your mathematics, you know that cosine of 90 degree gives us 0. Therefore, it gives us 0. Cosine of 90 is 0. Therefore, I dotted with j result in 1. In what? In 0. It gives us 0. I dot j gives you 0. J dotted k. The result between j is vertically upward. K is towards you. The angle between them is 90 degree. Therefore, it gives you 0. I dotted with k. I is acting on this direction. K is acting on this direction. The angle between them is 90 degree. I is acting on this direction and j is acting vertically upward. The angle is 90 degree. Therefore, always I dotted j, j dotted k, I dotted k always gives you 0. Keep this in your mind. Then let's try to find the dot product of the two vectors. Previously, we know that ax in the I, ay in the j, az in the k, dotted with bx in the I, by in the j, bz in the k. Let's try to multiply these two. xi can be dotted with bxi, byj, and bzk. And the same is true, ayj can be dotted with bxi, byj, bzk. But the only thing that we got is x, bx, I dot I, x, by, I dot j, x, bk, I dot k, and the like. The only thing that we got is I with I here, j with j here, and k with k. The other gives you 0 because you know that I dot j gives you 0, j dot k gives you 0. So this gives you 0, 0. It only gives us this, and this is 0 as well. this is 0, and this is 0. The only thing left is here, ax, bx, I dot I is 1. We know that I dot I, j dot j, k dot k is 1. Therefore, x, bx, ay, by, az, bz. So don't forget that whenever two vectors are given in a unit vector notation form, the dot product gives you just multiply the coefficients. Ax with bx, ay with by, az with bz. That's all. That's how we determine the dot product of the two vectors, and this results you in a scalar. Whenever two main quantities like force and displacement are the two vectors, if you are trying to multiply force with dotted displacement, the result gives you work, and work is a scalar quantity. Force is vector, displacement is vector. Whenever they are dotted with together, the result is work and scalar. But force and displacement, if they are in cross product, later we'll try to see about that, gives you another vector called torque, which is a vector quantity. So keep this in your mind. Previously, we have said that A dot P can be given as the magnitude of A, the magnitude of B, cosine of theta. The angle can be determined using cosine of theta is A dot B over the magnitude of A and the magnitude of B. A dot B, we know that it's possible to determine using this x, bx, ay, by, az, bz. Therefore, it's possible to find the magnitude, the dot product over the magnitude of each quantity gives you the angle between the two vectors. Let's see one good example. Here you have two vectors, and those two vectors are given as 5 in I, minus 4 in the j, plus k. And the other vector is given to be 3 in the j plus 6 in the k. Find the dot product of the two vectors. To determine the dot product of the two vectors, we have said that just try to multiply the coefficients. Here, 5 in I, 4, and 1 are the components. Okay? And here, there is no z component because that there is no k I component, what I mean, because that it says 3j plus 6k, the only y and z components. Therefore, we should have to multiply 5 with 0. Okay? If you are trying to put these components using component methods, column method, it's possible to find this 5 minus 4, and this one is 1. And the component of vector B can be given as 0. There is no I component or the component along the x-axis. And here you have 3 and 6. Therefore, to find the dot product, just multiply those respected components. I with I, j with j. Therefore, A dot B gives you 5 multiplied by 0, okay, plus minus 4 multiplied by 3, plus 1 multiplied by 6. This is how we determine. 5 multiplied by 0 gives you 0, plus this gives us minus 12, and this gives us 6. When you add these two, it gives you, okay, minus 6. Minus 6. So A dot B can be determined using just multiplying the coefficients of those respected components. It's also possible to find the dot products. Here you have vector P and Q, you have vector L and M, and so on. If you are asked to find the dot product, you have to multiply the respective components. What are the components of vector P? Well, here you have 3. There is no j component, therefore it should be 0. There is negative 1 component, minus 1. Okay? These are the components of P. The components of Q are minus 2, 4, and 5. Therefore, when you are trying to determine the dot product, you have to multiply the respected vectors, the respected components. 3 multiplied by 2 gives you minus 6. 0 multiplied by 4 gives you 0. And minus 1 multiplied by 5 gives you minus 5. Therefore, this is how we determine, just we add these two. The same is true here. The component of these vectors, L, vector L is minus 6, minus 8, and here 2. And the component of these are only negative 7. There is no j component, there is no k component, therefore these are 0, 0. Therefore, it's possible to multiply only these two. Negative 6 multiplied by negative 7. The rest, when you multiply, it gives you 0. Therefore, when you multiply this, gives you 42. That is the resultant vector. And always the dot product results you in a scalar. It gives you a pure scalar. And here, let's try to see some of the properties of dot products. Whenever you add two vectors, it's possible to find it's possible. Whenever you add A plus B, it's equals to B plus A. Okay, commutative property. Here you have identity property. A plus with 0 gives you A. Here you have the associative property. You can find this in lots of books. Therefore, you can read those. A dot B is the same as that of B dot A. Keep this in your mind. A dotted with A gives you the magnitude squared of those two vectors and the like. So you can see those properties in lots of books. Now let's try to see about the cross product of two vectors. Okay. So far we have seen about the dot product of two vectors. Whenever we multiply two vectors, might result in you cross product. Might gives us vector or a scalar. Previously, we have seen the dot product. Now, let's try to see about the cross product. The cross product. The cross product of two vectors result in vector. Okay. The dot product of two vectors gives us scalar. Now, let's try to see. Take two vectors A and B, as obviously, and the cross product of the two vectors, the magnitude of the cross product of those two vectors is given to be the magnitude of A, magnitude of B, sine theta. Previously, when we dotted product, A dot B gives us the magnitude of A, the magnitude of B, cosine of theta. That was how we determined the dot product. Suppose here you have two vectors, A and B, that we have said previously, and here we have angle theta. Therefore, the cross product of these two vectors gives us the magnitude of this vector, the magnitude of this vector, sine theta. Don't forget these two. Cos theta gives us scalar quantity. Whenever you have sine theta, it gives us a vector quantity. And this is the cross product. And the resultant vector is always perpendicular to those vectors, because the cross product of two vectors gives us vector, and that vector is always perpendicular to the plane where the two vectors made. Here we have vector A and B. Those two vectors can have a plane, okay, a plane, and the resultant of those two vectors gives you on perpendicular to both vector A and B. Okay, suppose here B cross A gives us perpendicular upward, which is perpendicular to both vector B and A. Look here, and here you have vector A and vector B. The cross product of the two vector, let's say it to be C. It's possible to use right hand rule. You have a screw rule or a right hand rule. Therefore, point A is acting on this direction. You can point this using your index finger, and point B or vector B is acting on this direction. You can point it with your middle finger. And the resultant is this one, that is the cross product of vector A and vector B is C. Let's say that C is a resultant vector, and C is perpendicular to this vector, and as well as it is perpendicular to this vector. For both vector, it's perpendicular. Here you have vector A and B. It's possible to use a screw rule or a right hand rule. Therefore, the resultant vector is always perpendicular to both vectors whenever you cross two vectors. But when you are having a dot product, the result is not vector, it's a scalar. Okay, you don't need the direction. And previously, you have used that I, J, and K are the unit vectors along X, Y, and Z direction. If you are trying to find the cross product of these two vectors, those three vectors, here I cross with J, the magnitude of I, the magnitude of J, sine theta. You know that the angle between I and J, I is acting along the x-axis and J is acting along the y-axis. The angle between them is 90 degrees. Therefore, sine 90, you can have sine 90 is 1. Therefore, I cross J, it's the magnitude, not the vector itself. The magnitude gives us 1. I cross I. Okay, if you try to cross those two vectors, we know that I is acting along the x-axis and another I is acting along the x-axis. The angle between them is 0 degree since they are overlapping to one another. Therefore, the magnitude of I, sine theta. We know that the magnitude of I is 1, the magnitude of I is 1, but sine 0 gives us 0. Therefore, I cross I gives you 0. J cross J gives you 0. K cross K gives you 0. But I cross J, the magnitude of I cross J is 1. The magnitude of I cross K is 1. The magnitude of J cross K is 1. And the reverse is also true. But we are talking about the magnitude, not the vector itself. Okay, keep this in your mind. I cross j gives you the same as that of j cross I. Note that we are talking about the magnitude. I cross j is the same as j cross I cross k, k cross I, j cross k, k cross I, all gives us 1. But if you are trying to determine the direction of the resultant vector I cross j, I is acting to what direction? To the x direction. This is I. J is acting to the y direction. And the resultant of the two vectors, I is acting on this direction, j is acting vertically upward. And the resultant using right hand rule is you have to point your thumb, and your thumb points to the direction of z axis. Therefore, the resultant of I cross j is k, okay? K. And it's very easy to recall this using a simple technique. Here you have I, j, and k. The cross product of I cross j gives you, using right hand rule as we have seen previously, gives you k, okay? And j cross k, if you j crossed with k, the result gives you I, okay? And k crossed with I gives you j. And take that when you are trying to move clockwise, positive. The result is positive. That means I cross k gives you, I cross j gives us k. But if you are trying to reverse back, like j cross I, that means counterclockwise. From j, if you are trying to reverse back counterclockwise, it gives you the negative of k, okay? Negative k. If you are trying to cross I counterclockwise with k, the result gives you negative j. And keep this in your mind. It's so easy how we determine the cross product of the unit vectors. And for two vectors A and B, it's possible to determine the cross product using a matrix method. I hope you have learned this in your mathematics lesson. Using matrix or determinant method, it's possible to determine the cross product of those two vectors. Let's take vector A and B. The component of vector A is x, ay, and az. The component of B is bx, by, and bz. You have to put I, j, and k in a square bracket or in a line, parallel lines. Ax, first you have to put the component of A, ax, ay, az. Okay? Don't reverse those two. You have to put the value of A first, then B, bx, by, and bz. Then the matrix said that first you should have to eliminate the I, colon, and row. The result will give you this. I, if you eliminate those two, the left ay, by, az, and bz left here. So we can see that ay, by, az, and bz. The other technique is for j, you should have to eliminate these two, the colon of j and row of j. You can find it to be az, bz. And after all, it's possible to multiply these two, ay, bz minus az, by plus j, az, bx minus x, bz, and so on. Okay? Therefore, it's possible to determine the cross product of those two vectors. And the result of A cross B gives you a vector here. Look at it. You have I, j, and k. And it represents the direction. I is the direction along x, along y, and along z. It shows us the direction. And it is a vector. The cross product gives you vector. And the dot product gives us scalar. Keep this in your mind. Let's see one good example here. Here you have 2 in the I plus j. And let's try to determine the cross product of those two vectors. Here you have vector A. If you are trying to multiply, this is a scalar, and these are vector I and j. You can distribute these two as 2 in the I plus 2 in the j. And you have vector B here, 2 in the I plus 3 in the j plus k. it's possible to find the cross product of these two vectors. If I say find the cross product of the two vectors, you have to put it in matrix like I, J, and K. You have to put all the components of vector A as 2, okay, and 2 in the J as well. But here you don't have Z components, meaning it is 0. And here you have vector B, which is 2, 3, and 1. Whenever you are trying to determine the matrix or the component of this, the cross product of these two vectors, first put it I into as, or you can put it in a square bracket. You can eliminate the row and column. You can eliminate this. You've left with that of 2 and 3. Here we have 0 and 1. You can put plus or minus actually. If you put minus in the J, you can eliminate the row and the column. The row and column. Therefore, you have to use 2, 2, and 0, 1. Okay. Here you have to put minus. Whenever you put in the I first and the K component, you can put minus. If you put plus, some books use plus J. If so, you have to put K first. Okay. 0, 1, and 2, 2. Okay. Then plus. The usual technique is to use minus. And the K component, you can eliminate the row and column of the K. You can find it to be 2, 2, and 2, 3. Okay. The rest remains the same. Therefore, the resultant gives us I. You have to multiply 2 by 1, 2, minus 0 by 3, 0. Okay. Minus J. Okay. 2 multiplied by 1, 2, minus 2 times 0 gives you 0, plus K. 2 times 3 gives you 6, minus 2 times 2 gives you 4. And at last, this is 2 in the I, and this gives us minus 2 in the J, and this gives us 2 in the K. This is the resultant of vector A cross B. This is the resultant vector, and let's say that this is vector C, and vector C is perpendicular to both vector A and vector B. This is how we determine the cross product of the two vectors. It's also possible to find the magnitude, its magnitude. The magnitude of the vector can be determined by squaring each quantities. 2 squared plus 2 squared plus here minus 2 squared plus 2 squared. This is how we determine the magnitude of the two vectors. So this is all that I've got for today. Next time we'll try to see some of the applications of vectors. So see you then.